Hey, it's Ben, and this is Lecture 1 of Open Project Space. We're going to talk about electrical engineering and embedded systems. And now what's core to this program, of course, are embedded projects. So we're going to start by explaining what an embedded system fundamentally is. And then we're going to discuss the basics of circuits to help you build the core understanding you need to develop the accompanying project of this lecture, which is an LED circuit. And so we start with, I think, a reasonable question. What is an embedded system? Well, an embedded system is a combination of hardware and software designed for a specific purpose. Take, for example, an alarm clock. An alarm clock is a single system which is designed just to tell you the time. And it allows you also to set an alarm. And of course, hopefully that alarm rings when you're supposed to wake up or when a meeting's about to start, but that's its only purpose. The same is true for a watch, a wristwatch. All you do is read the time off it. You maybe set alarms. Now, we also have, for example, a camera. Cameras take photos. That is the specific purpose. Or maybe, bear with me, we go back in time 10, 15 years ago, and you had an MP3 player. That MP3 player's job is to play MP3 music. That's its only job. And this contrasts from a general purpose system, like a smartphone or a laptop. You have these devices and you know they can do more than one thing. They have a set of applications. Often you can take an alarm clock and set it within your phone. It's a camera as well. It's a media player. You can watch YouTube on it. You can scroll through Instagram Reels. It's a general purpose system. The same is true for a laptop. You can play video games off it. You can run an internet browser. These systems are used for multiple applications, and they typically have much more functionality than an embedded system. And so let's use that as our working understanding of what an embedded system is. So can you think of some more examples of embedded systems? And I invite you to go back to these lecture slides and come up with some ideas, and then click on this link here to see if your ideas match the list of examples. Or maybe it'll give you some inspiration or better understanding of what other embedded systems look like. So large-scale mechanical and electrical systems often contain multiple smaller embedded systems, and each embedded system has a function that supports the larger system. And so my favorite example here is an airplane. Airplanes are a wonderful example of systems engineering where multiple embedded systems are responsible for many aspects of a passenger's flight, of the pilot's navigation and steering of the plane. So for example, we have an in-flight entertainment system. That's one system that's designed to show passengers movies. They can play games. We also have temperature control, speed control, flight management, flight data recorder, and there's plenty more. And again, each of these is an individual embedded system, and they all communicate with each other to keep the airplane running. And so that is what embedded systems scale up to. You won't see that as much in our projects. We're not setting out to make an airplane here. That would be well beyond the complexity of this course. But that is where they're applied at this scale. In Lecture 4, we're going to discuss the architecture of embedded systems in the context of Arduino. You're going to use an Arduino board to build projects. But for now, we're going to focus on the physics and circuits principles that govern embedded systems. And so for your first two projects, Project 1, which accompanies Lecture 1, Project 2, which naturally goes with Lecture 2, we're not going to discuss circuits with Arduino or other microcontroller boards. We're going to stick with more basic designs. All right, let's talk about the science of electric circuits. And that conversation begins with energy. You might remember this from physics class in high school or maybe a college course. Energy is the ability to do work. And we have potential energy and kinetic energy. Potential energy represents the energy stored in an object that has the potential to become another form of energy, which is usually kinetic energy. Now, kinetic energy is the energy associated with an object's motion. Take, for example, mechanical motion, wheels turning on a car. We have radiation or light emission. This would be the movement of photons coming out of a light bulb. We have electron flow, the movement of electrons to generate electricity, which we're going to cover in a little bit. And now let's jump back to that concept of work in our original definition of energy. Work is the change in kinetic energy in a system. Work creates motion. And so if energy is the ability to do work, we require energy, potential energy, to transfer into kinetic energy to create motion. So let's try to think of some different types of potential and kinetic energy. We still have light emission, for example, but there's also nuclear energy. What are some other types of energy that you can think of? And I invite you to, of course, go back to the slides and click on this link, compare your answers to the examples we provide, and maybe you'll see some other forms of energy that you didn't quite consider initially. All right. And now this concept might be the most abstract of our discussion today, but I want you to consider entropy. Entropy, there are many definitions, but for our sake, in the context of our discussion, I'm going to describe it as the dispersion of energy in a system. The higher the entropy of a system, the more energy is randomly distributed in the system. Now, the key phrase here is nature favors systems with higher entropy. That actually increases the stability of a system. And in stable systems, then, energy must be more randomly distributed. And so what we see in systems of increasing entropy is that the potential energy of bodies in the system is reduced and dispersed as other forms of energy, like thermal energy. So take, for example, the laptop that you might be watching this video off of. That laptop has within it a battery which stores chemical energy. This is a form of potential energy. It's a very high density form of potential energy. And that chemical energy is converted into electricity. That electrical energy is eventually converted to light that emits from the display and is dispersed across your room. That electricity is transformed into sound, the sound that plays from the video right now that you're listening to, and that is also dispersed in the room. And eventually, when that energy, that chemical energy is spent and your laptop dies, the result is that all that energy, that light, that sound has been emitted across, say, the room you're in and dispersed. And eventually the light becomes heat as it's absorbed by bodies and other particles in the room, and the same is true for the sound. So again, we see all that potential energy has been reduced and dispersed. Now, this concept of entropy is going to come back in a couple slides, but I just want you to remember that nature favors systems with higher entropy. All right, let's talk about our star in the discussion of energy, electrical energy. This is the energy associated with charged particles. Charged particles include, but are not limited to, protons and electrons. But we're going to be concerned mostly with electrons. Still, electrons that are not in motion, are pretty boring. But electrons in motion will generate what we call electricity. Current is the flow of charged particles, usually electrons. And when we've got current, we've got electricity. Current has a magnitude, which is measured in amperes, and it also has a direction. And an important concept to remember here is that while electrons flow in one direction, we've measured conventional current to flow in the direction opposite to the electron flow. And this might be a familiar story if you've taken a physics class already in maybe electricity or magnetism, but a long time ago we assumed that it was in fact protons that were in motion. So that was our mistake there. It was in fact the electrons that were in motion. So remember again, conventional current flows in the direction opposite to the electron flow. And when we measure our circuits and do our debugging and troubleshooting, we're going to use the concept of conventional current. But what generates current? We've got electric potential. It's the amount of work needed to move a charged particle between 2 points, and this is measured in volts. Let's consider a 2D space in which there are points of higher electric potential and points of lower electric potential. And we have a charged particle in one of the points of higher electric potential. What is it going to do? It's going to move from the point of higher electric potential toward the point of lower electric potential. Why? Well, remember that concept of entropy. Nature favors systems with higher entropy, where energy is more dispersed. If that charged particle moves from a point of higher electric potential to lower electric potential, energy will be expended and dispersed in the system. And this means that electron flow or current is generated when there is a difference in electric potential between 2 points, when there is a point of higher electric potential and a point of lower electric potential. All right, building up here. Now we've got voltage, not to be confused with volts. Voltage is the electric potential difference, the difference in electric potential. Those are the same things. Current can flow where voltage exists, where an electric potential difference exists. And not to be confusing, it's measured in volts. Because if we jump back to the previous slide, you'll see that electric potential is measured in volts. If we're measuring the electric potential between 2 points, which is the difference, that's subtracting one electric potential from another. And so the units are still the same, the volts. Batteries are an example of a voltage source. There is a difference in electric potential between the 2 terminals of the battery. We have one terminal, the positive terminal, and one terminal, the negative terminal. And when these 2 terminals are connected, current will flow. Why? Because the positive terminal has a higher potential than the negative terminal. And so again, the electrons will be inspired, let's say, to flow to the lower potential, to increase the entropy of the system, to change that potential energy, convert it into kinetic. And again, the electrons will be happier at the negative terminal because nature favors systems of higher entropy. So how do we measure voltage? This is an important concept for down the road. Measuring voltage requires a reference point. Why? Because remember, voltage is electric potential difference. It's a difference in volts between 2 points. We have one point, let's say the positive terminal of our battery, and to find the difference in volts between that point and say our negative terminal, we need to define our reference point as our negative terminal. And so when we've measured the voltage, we find that the difference in volts between the 2 terminals at the positive terminal is positive 9 volts. What's the voltage at the negative terminal? It's 0. Why? Because the difference in volts of the negative terminal relative to itself is 0 volts. It's the same point. There's no difference in volts. It has to be 0. And so this is true for all measurements you'll make. There is no voltage at the same location as the reference point. All right, that reference point that we've been talking about, in this case, it's our negative terminal of the battery. That reference point we call ground. Again, this is the working concept we'll have for now. It gets more complicated, as most things do, but for now, we're going to call it ground. Let's talk conductors. Current cannot flow without a path for the electrons to move. So we have conductors, which are materials in which electrons can move freely. If a voltage exists across a conductor, current will flow. Current will flow from the point of higher electric potential in the conductor to the point of lower electric potential. And so we have these materials, these nice images shown on the right, gold, copper. These materials are common conductors. They very easily allow electron flow. And so again, I mentioned copper, I mentioned gold, there's silver, there's aluminum, but one of the cheaper materials, while still being very conductive, is copper. And so that's what a lot of our components, our wires will make use of, is copper as a conductor. Let's talk about resistors. Resistors are a component that reduce the flow of current. Resistance is measured in ohms, and it's the ability to resist current. All right, we've arrived at circuits. A circuit is a closed loop path where electrons can flow. An open circuit contains a discontinuity that disrupts the electron flow, the current flow. Take, for example, this circuit to the right. We have a switch, there's a battery, our voltage source, and then an incandescent bulb. This switch is open. There's no closed path for current to flow. And so as long as that switch is open, the incandescent bulb will not be powered. Now let's say this circuit is closed. It has a fully continuous path, meaning the switch must be closed. Then current will flow from the positive terminal of the battery through the incandescent bulb, through the switch, back to the negative terminal, and the bulb will be powered. All right, we've talked about open circuits, we've talked about closed circuits, what a circuit is in general. We've arrived at one of the most important concepts you will learn in this course and in all your time in electrical engineering. That is Ohm's law. V equals IR. This relates the voltage, the current, and the resistance in a circuit. If we hold voltage constant, if V stays the same, and we increase resistance, then current must decrease. And in the opposite case, where voltage is still held constant, if resistance decreases, then current must increase. And this may seem a little bit abstract right now, but we're going to see this concept applied in our circuits later on. And it's going to help you debug them. We'll see it in a little bit. So let's talk about building DC circuits. And I think an appropriate place to start with this is the question, what are DC circuits? What are AC circuits? Because if we're talking about DC, we have to talk about AC. Now, this course's projects focus on direct current, or DC circuits, where the voltage and direction of current is held constant. Take, for example, this graph down here of a direct current. Across the y-axis, we have the voltage. Across the x-axis, we have time. And you can see as time progresses, the voltage is constant, and the direction of current is also constant. The direction of current is indicated by where the line rests on the graph. Is it on the positive side of the axis, or is it on the negative side of the axis? If the current is negative, it would be here. If the current is positive, it would be here. But no matter what, the current is constant. So across the full period of time, the voltage is on the same side of the axis. We have other circuits which rely on alternating current, or AC, where the current's direction oscillates back and forth. Take, for example, this graph of alternating current, where the voltage, again, is on the y-axis, and on the x-axis we have time. Voltage is oscillating above and below the axis. The current's direction is oscillating from positive to negative. This is fundamentally alternating current. Let's break down that concept of circuits into three components. Think back to the first circuit that I showed you, the switch, the battery, and the light bulb. We had a voltage source to provide electrical energy and to generate current. Now, it could have been the battery, like we had in that example, but we could have also had a DC generator. Solar cells are another voltage source. We also need a conductive path to flow. Those red copper wires were our conductive path between the components. And within the components, there was also a conductive path. And that's where the current flowed. We had the wire. Take, for example, circuit board traces. Those are conductive. We'll talk about what circuit boards are later. And occasionally, air. Take, for example, lightning. Electrons can flow through air. And now, at last, we need a load to expend the electrical energy. In that circuit I showed you before, that was the light bulb. It could be a sound speaker. It could be motors. And occasionally, in the case of lightning, you might be the load. The current travels through you, is expended on you. And hopefully, you will be okay in the end. Okay, we talked about components. Let's talk about polarized components. A polarized component is one which can only be connected to the circuit in one direction. Batteries have a positive terminal and a negative terminal. The current will only flow from the positive terminal to the negative terminal, so it can only be connected to the circuit in one direction, typically. We have LEDs. We'll talk about those later. These emit light. They are polarized. We have electrolytic capacitors. We'll talk about those in the next lecture. Again, those are polarized components. These components have typically a positive and negative terminal. Remember that current flows from positive to negative. This will usually be their insight into figuring out how to place the polarized component in the circuit. And these terminals on these different components may be distinguished by lead length, by labels or notches on the component. You'll find that one terminal, maybe the positive terminal, might have a longer lead than the negative terminal, or that a notch will be on the side of the positive terminal, but not the negative. And so sketches of the circuits will indicate these polarities as a sort of reference to you when you're actually building the circuit from the schematic, from the sketch. LEDs. We mentioned those earlier. Now we get to tell you what they are, if you haven't already heard of them. They're light-emitting diodes, LED. A light-emitting diode, big whoop, is a component that emits light. And as a diode, the LED is polarized and has a constant forward voltage between its anode and its cathode terminals. So if we look on the right, we've got the LED. One terminal, the longer lead, is called the anode. This is the positive terminal. We've got another lead, the shorter lead, where the flat side of the LED is. That's the cathode. And current will only flow from the anode to the cathode. Because the LED is a diode, it's polarized. Current only flows through one direction, from anode to cathode. And again, it has a constant forward voltage, which means the voltage drop, the voltage across the positive terminal, the anode, to the negative terminal, cathode, will usually be the same as long as you stay within its normal operating conditions. So if the voltage starting at this terminal was, say, 3 volts, then once you arrive at this terminal, the voltage will have dropped by 2.2 volts to 0.8 volts. So if you need to figure out what the normal operating conditions of the LED are, you're going to refer to its data sheet, which may have come with the component when you bought it. And this is where you'll find the operating conditions. Now, there will be a recommended operating current. What's the typical current that should flow through this LED so that there's not so much current that the LED burns out, and so there's not too little current that the LED doesn't emit light. It'll also tell you the forward voltage. We said this red LED could be a 2.2 volt LED. It could be 3.2 volts. It could be something else. And the data sheet will indicate that. All right, what is a data sheet? The manufacturer of a component or device creates a data sheet to document its characteristics and operating conditions. So common features of the data sheet will be some kind of summary to describe what the component is and what its basic function is. It might have a functional block diagram or schematic diagram. It might have a pinout diagram, a recommended set of operating conditions, graphs, truth tables, or timing diagrams. Now, not all of these terms will ring a bell right now, or maybe they do, but for this lecture, we're just going to focus on the summary and the recommended operating conditions. Later, we'll talk about what pinout is, how to read truth tables, how to read timing diagrams, and what a schematic diagram looks like. All right, the summary. So on the left, we have an example of a LED data sheet. And on the first page, it has just a short description of its main features. That's low power consumption. It has general purpose leads. And it also has a description of the LED. It's a red LED. And of course, it's a light emitting diode. And then it also happens to feature dimensions of the component. So in summary of the summary, it will include a description of the device and its features. It may also include a high-level schematic of the device with its dimensions, the diameter of the LED, the length of its leads, etc. All right, and so another page will discuss the recommended operating conditions. And this section of the data sheet will usually contain suggestions for the current or voltage as input to the device. Sometimes it doesn't say it outright. Instead, it shows you the absolute maximum ratings, which are the limit for operating the device safely. And here is an example of that. We have the absolute maximum ratings for our red LED. Let's try to find the current. I'm going to look at the left side of the table where it shows our list of parameters. We found DC forward current. Now, let's say we're building a simple LED circuit. We're going to be using a DC current. And here it says we want our maximum current to be 30 milliamps. If we go much higher, I suspect the LED will burn out. And so we would also want to find the expected voltage drop at this maximum rating or lower. And actually, that would be up here, the forward voltage. And the forward voltage of our super bright LED will be a maximum of 2.5, or somewhere around 1.85. But we'll take it to be somewhere in between, maybe like 2.2. And these are under the test conditions of 20 milliamps. So in fact, we don't even need to refer to the maximum ratings here and try to guess what's a reasonably lower value. It tells us right here. Let's use 20 milliamps because under those test conditions, we'll get a voltage drop somewhere around here, 1.85 volts. Okay, so we talked about LEDs. We talked about reading an LED data sheet and a data sheet of similar components. And so now let's talk about resistors. We might, as we've determined from the data sheet, need to control the current of our circuit to bring the LED under normal operating conditions. And to control our current, to lower our current, we might need to increase the resistance. And we'll do so with an axial resistor, which have a lead at either end of the resistor. That's what they look like, lead on either side. And so we can actually look at, say, this 4-band resistor and decode its resistance from its colored bands. So let's look at that 4-band resistor. If we were to look at the first band, that actually represents the first digit of its resistance. If we examine the chart here, that would be 1. Let's look at the second band. That's the second digit. Second digit is black or 0. The third band is the multiplier. That's red. So if we go over and look at our chart again, we see that's 10 to the power of 2. And so if we take our digits, combine them, and multiply them by their multiplier, we get 10 times 10 to the second, which is 1 kiloohm. Now what's this number right here? Well, that's the tolerance, which we can find from the 4th band. The 4th band tolerance. And if we go to our chart, this fourth band, which is gold, we'll see that the tolerance is plus or minus 5%. What does tolerance mean? The tolerance is the maximum deviation of the nominal resistance from the true resistance of the resistor. And so you might take this 1K ohm resistor, measure it, and find out that it's actually a little bit lower. It's 990 ohms, or maybe it's a little higher. It's 1010 ohms. And so higher quality resistors will tend to have lower tolerances, plus or minus 1% instead of plus or minus 5% or 20%. So we're gaining ground here. We've talked about LEDs. We've talked about resistors. We've talked about voltage sources like batteries. We are slowly assembling the knowledge we need to build a simple LED circuit. But we're missing something, and that something is a schematic. We need a schematic diagram which defines the connections between components in a circuit to inform us on how to build the circuit. Schematics also summarize the component's values, and each component has a unique symbol associated with it. Let's take, for example, the schematic on the right here. We don't need to know what it does, but we can see that each symbol is unique and that a component is uniquely assigned to it. And each symbol also has values near it to summarize the component's values. And between each symbol is a connection of some kind. And so let's take this symbol over here, this component. It has the value 9 volts. And I can infer from that, let's say I didn't know what the symbol was. I can infer from that this is probably a voltage source of some kind. It's probably a DC voltage source, and it is supplying 9 volts to the rest of the circuit. And in fact, this is a battery. And what you'll find on this next slide is a nice reference for you of what each symbol is associated with. We've got the battery symbol, there's a voltage source symbol, a ground symbol. Remember, ground is our reference point. So if you were measuring voltage at a certain component, it would be in reference to wherever ground is on the schematic. We have resistors. There are 2 different symbols. One is the US resistor symbol, and one is the resistor symbol that you would see more often in, say, Europe. We have the same thing for potentiometers. You don't need to know what this is right now, but it'll come up. We've got, again, the US potentiometer, and then the one that everybody else uses. We have switches. They have different symbols. When a switch is open, it'll look like this. When a switch is closed, it will look like this. We might have a 2-way switch. And so there will be one input terminal, and the current can flow either through this terminal here or this terminal down here. We have push buttons, literal buttons. You press down the button and a connection is formed and current can flow, or the button is not pressed and current does not flow through the push button. We have speakers which emit sound. We have DC motors. You know what motors do. And then, of course, we have the LED symbol. Remember, LEDs are polarized. And so one side of the LED will be the positive terminal, and the other side will be our negative terminal. And you'll always know, based on the LED symbol, which side is positive and which side is negative, because the arrow of the LED, and this is actually inside this circle, is a diode symbol. This arrow points in the direction current will flow. And since we know current flows from positive to negative, we know that the positive terminal must be on this side, and current flowing in the direction of the arrow leads to our negative terminal, which is on the other side. We have more symbols here. We have connected wires, which are represented by actual nodes, let's say dots. And so we know here that current can flow across, can flow into this node and then up or down. Same idea here. Current can flow anywhere between these connected wires. And then we have unconnected wires. I'd say the best practice for you when drawing two unconnected wires which cross over each other is to draw it so that there's a little bump. And then it makes it clear that they're not connected. They're actually just crossing over each other. And you can see there's some more ambiguity in these because it doesn't have that little bump. And so I wouldn't recommend drawing your schematics this way, but you might see this in some of the schematic diagrams that you interpret. And so you should know these aren't connected, that typically there will be some sort of node or circle to indicate that two overlapping wires are not in fact overlapping, but are connected. All right, Ohm's law. Seems like we learned that ages ago, but now we're actually going to apply it. We have a circuit diagram. There's a voltage source and there's a resistor. The voltage source here is a 9-volt voltage source, and the resistor is of an unknown resistance. But we happen to know the current that is flowing through our circuit. It's 2 amps. And so I want you to obtain the value of the resistor, knowing Ohm's law, V equals IR, and these initial values, the voltage and the current. I'm going to give you a moment to pause, so you should do that right now and find your answer. All right, you should be back with your answer, and that answer should be 4.5 ohms. You plugged in your voltage, that's 9. You plugged in your current, that's 2. We take voltage and divide it by current, 9 divided by 2, and we get 4.5 equals R. So our answer is 4.5 ohms. We're so close to assembling our LED circuit, but we need to prototype it somehow, and we'll do so on a breadboard. It's a reusable board for prototyping our circuits, and inside the breadboard are conductive metal strips. And so when you insert components into holes of the same strip, current can flow between those components. Let's look at the diagram on the left. We have holes. Horizontally, these holes are connected in a strip, so current can travel freely across one of these strips. It's important to know that strips are isolated electrically by what we call the channel of the breadboard. We have holes that can be arranged horizontally across the channel, but the holes are not fully connected across the channel. We have one strip here and one strip here. And when we arrange components in the holes, we will put one terminal on one strip and the other terminal on the next strip. We have vertical strips that are connected down the entire board. These vertical strips are called our power and ground rails. When you have a voltage source, what is common is for you to put the positive terminal of the voltage source on the power rail and the negative terminal on the ground rail. And then using a wire, jumper wires, you would connect these holes to whichever strips, horizontal strips, that you're using on your breadboard. So these are the basics of breadboards. You'll see them described a little bit more in Project 1. And we have one last concept to cover, which is soldering. So final circuit designs are often soldered onto printed circuit boards, which are called PCBs, or perf boards. Now, printed circuit boards might look familiar. These are often used in the electronics you have around your house, inside that alarm clock you have, inside your phone, your laptop. These can be mass manufactured, and they can be done cheaply. We also have perf boards. These are more often used by hobbyists. And so what is soldering? It's the process that joins circuit components together. And we do this with a filler material called solder. Now, I'm going to be brief here because we have a workshop to cover this. But what you'll see in the photo on the left is that we have a tool called a soldering iron. We have that filler metal called solder. And what this person is doing with their massive hands is applying solder to a pad on the circuit board. It's a conductive pad where the terminal of a component is And so when the iron, which is really hot, is applied to the pad as well, it melts the solder and it joins the terminal of the component to the pad. And when that solder is cooled down, it is very difficult to dislodge. And so this is a much more permanent way to build your final circuit. And that's it. Again, we will cover soldering more in the workshop slides, which you can find on the OPS website. I invite you to look back at the slides again if you haven't already, to go through those interactive questions, to click on the links to explore those topics just a little bit more, or to rewatch this video. Thank you for watching. I hope you have a wonderful morning, evening, or night, whatever time it is, and I'll see you in the next lecture.